most of you seem to have come to the right place. Step one, let's take that as a positive first step, okay? So since you don't know why you're here, which is sad, I've decided that I'm going to talk to you about software-defined networking. Now, if that's not what you want, you could get up and leave right now, but that would be very hurting. It would make me feel very bad. So now you have to sit here for like the next, I don't know, 45 hour minutes, whatever, and listen to me talk about software-defined networking. So there you go. All right. Software-defined networking is a big deal. So already you know about software-defined networking. You know that the acronym for it is what? Okay, my work here's done. Thank you very much. Feel free at the next cocktail party you go to, just feel free to drop Sdn, and all of a sudden you're going to sound like a really smart person who knows what's going on. All right. What's interesting about the networks that have been built today? By the way, quick show of hands, who uses networks? Are there any hands? Come on, come on! YouTube, Gmail, come on, you're all using networks. No, well, okay, I can occasionally, but I don't talk about it. Yes, so we all use networks, right? Do you realize that the networks that you use today are basically old, stinky networks? When were they designed? When were the basic concepts that went into the networks that you use every single day? When were those first concepts laid down? Late 80s, maybe 95, 96. No! It was in the 70s. It was way back in the 70s when they figured this out. Interesting things that they did, they made some guesses. Because when they were first putting networks together, they had no clue because networks didn't exist. So they made some guesses. They said, hey, how many bits should we use for network addresses? A bunch of guys sitting around drinking the beer saying, 8, 16? They said, I'll tell you what, 32. There's no way we'll ever exceed 32. I mean, come on, really? There's like, 8 servers in the world at this point in time. 32 is good enough. And, it turns out it was a pretty good bet up until February of 2011 when we ran out of internet addresses. IP4 addresses were all gone, right? I think they got like about 16 million addresses is what you get out of 32 bits. Great idea, but it was wrong, right? When they first came up with the concept of networks were static things, right? You would build a network. It was a box. You put the box in a room. You ran some wires to it. End of story. What do we have today? What kind of machines begins with a V? Virtual machine, right? Virtual machine, where does a virtual machine live? In a virtual world, or even better, in the cloud. No matter what, a virtual machine can move around. Physically, a virtual machine can move from box to box to box. So the concept of a network being a fixed thing, a static thing that doesn't change, that's gone, right? So those networks that we used to build, that was a box here and a wire that connected to this box, and there's my network, all of a sudden that's an old idea that's actually out of date. What that means for us is that it's time to come up with a new idea. So, in our time together, I want to cover 3 things. Number 1, I want to introduce you to the idea of SDN, software-defined networking. I want to make sure that by the time you leave today, you know what it is. You understand the basic concepts behind it. Once again, we're getting you ready for that cocktail party. Okay, that's the most important thing. Number 2, we're going to talk about Google. We all know who Google is. Google's a very wealthy company. Google's entire operation is based on networks, okay? Because they have deep pockets, because they've got really smart people who work for them, they are very interested in making their networks work better and better and better. They've become extremely interested in software-defined networking, and they've done some very revolutionary things. We're going to be talking about what they did. And we're going to wrap things up by talking about, what else? The future. So software-defined networking is brand spanky new. We do not have all the answers. This is a hot area of research. That means that people are finding their way. We're in a dark room and we're trying to figure out what else is in that room with them. So if you're looking for research topics, if you're looking for businesses to start up, if you're looking for any of those sorts of things, Sdn is a fantastic place for you to spend some time because the answers are not known yet. We're just at the start of this particular journey. So, I can sit here and tell you, oh, wow, that's a big thing, but stop. Don't listen to me. Read the Wall Street Journal. So this is an article out of the Wall Street Journal about 2 weeks ago. AT&T targets flexibility and cost savings with new network design. Guess what that new network design is? AT&T, an old, stodgy company that has very large and somewhat brittle networks, is looking into SDN, okay? They're actually making steps, they're talking to their vendors, they're getting ready to change how they buy products because of SDN. It's changing everything. The reason they're doing it is because the way AT&T does things today is too expensive. Every roughly 18 months or so, there's new shiny Cisco hardware out there. So AT&T has to go out to their network and has to rip out everything they put in just a little while ago and buy brand new gear and deploy it in the network. Fantastic business for Cisco. Woohoo! Bring it on. Well, better stuff for you in a year and a half, right? But a horrible business for AT&T because it's eating up their profit, right? So AT&T is desperately looking for a different way to do it. Cisco doesn't stand still. Cisco has an SDN story. But what's interesting is AT&T's not buying that story. So the world's getting ready to change. If you're planning on going to work for Cisco, if you're planning on partnering with Cisco, you might want to wait and see how this will play out. Because it's going to change. We couldn't have an SDN presentation unless we had a network. So here you go. Here's your network. All right. What do we have in this network? We've got 6 circles. Yay. Circles are always routers. Okay, so we've got 6 routers in this network. We have 4 users. 1, 2, 3, and 4. And they all want to talk to user number 5. It's hidden over there in the lower right-hand corner. This is a pretty typical network problem. These users connect to routers. Those routers connect to other routers. When user 1 says, I'd like to talk to user number 5, his router talks to another router and says, hey, there's a path between us. That router says, fantastic, there's a path between me and another router, and eventually one of those routers is able to get to user number 5. So when user number 1 sends information over the network, there's a path for that information to go. It's a little hard to see on this particular chart, but each one of these paths actually has a number associated with it. They all have different capacity. Right? So I'm, just sending a huge video file or something like that. A particular path may or may not have enough capacity to handle what I'm sending. So you always have to work that into what you're doing. Awesome. Next slide. So when all these users start making requests to talk to number 5, the network starts to take a look at what's going on. What's interesting, and this is how today's networks work. This router here just sees this world. It just really sees router C. So it will pass all of its packets, all of its data to router C. Router C actually sees a world that has router D, router E, router A, and router B. So when it receives packets from A that are going off to E, it's got a couple of different paths that it could take. Each router just sees the world that it's connected to. But somehow, using logic that's built into it, they're able to come up with a way to connect all these users to user number 5. That's what the dash line is. Now, what's interesting about the dash lines is, yes, they're good because they connect our users to user number 5, but they may not be optimal. Okay? Depending on what the user is, depending on what their application is and stuff like that, they're good because they are connections, but they may or may not be optimal. Uh-oh. We lost our connection. All those connections were traveling over that one link, and now that link just caught on fire, fell apart, something else loved it. Who knows what happened? But it broke. So what's going to happen to our connection when that link breaks? We hope it's going to reroute. No matter what, immediately you're going to lose your connection, though, right? You're cut off. You're watching Netflix at home, and bam, the movie stops. Oh, I hate it when that happens. Okay. So what's going to happen? All these routers are going to be notified that there's a broken link, right? Okay. Now, what they're going to have to do, specifically router E, which is the one right there, it's going to have to find another way to get to router F. How many other routes does it have? So it's got 3 other routes it can take. Next one. Yay! It found another route. Oh, wait a minute. All 4 connections attempted to build a path over the same link. There's not enough capacity on that link for all 4 connections to be there. So guess what? Somebody wins and 3 lose. Who wins? Whoever got there first, right? Yeah, you win. Okay. The other 3 lost. What do the other 3 have to do now? They gotta do it all over again, right? They're gonna go looking for their own particular path. Okay? Next slide. Yay! Everybody found a route to 5. That's fantastic. Problem solved. Life is good. Or is it? So everybody has a route to 5. That's good. But what do we know about this? Are they optimal? What's going to happen if the users start to send bursty traffic? And more important, is there any delay associated with any of these particular routes? You know, if I'm doing something that's very interactive, I'm playing a game. So I got to storm the building, I got to go up to the 3rd floor, and I got to shoot the Dark Lord. Well, if I open the door and then I have to wait for it to redraw the screen, and then I storm in, and then I have to wait for the Dark Lord to be redrawn on the screen, you know, my game enjoyment's going straight down, right? So latency may be a huge issue for me, okay? And if the path that just got reset up for me doesn't have a good latency value, I'm going to stop playing and somebody's going to lose revenue based on that. Okay? But this is the situation that today's designers find themselves in. Okay? Congratulations. Network's smart. It's able to rebuild itself. But the paths that are built may or may not be optimal paths. Next slide. So what's this SDN thing all about? Okay, in a nutshell, SDN promises to make high-capacity networks cheaper and easier to build. Okay? We're going to be able to reconfigure them on the fly. Now, a traditional network, what's it made up of? Routers, switches, bridge, and lots of cable, right? Okay? And we lay them out, and we connect them together, and we say, that is our network, okay? It's defined in a particular direction. It's designed to allow information to flow around a particular organization. When you're designing a network, it's very similar to designing a highway. You had better get it right the first time, because it's going to be a pain in the butt to move, to change, to reroute, right? You connected those two servers in that particular way. Don't make me have to come back and redo it because you got it wrong, okay? Networks do two things. Number one, they deliver data, of course, okay? And number two, they manage the flow of that data. Bursty data, low latency data, et cetera, et cetera. So things change in a software-defined network. What happens in a software-defined network is that we're going to take control of what's going on out of those routers, and we're going to put it in a centralized location. You can't actually read it, but this is a Cisco Nexus 5596T. It is a very nice router. If you needed a router, this would be a great one to go on Amazon.com and buy. You would be spending about $27,000 to buy this particular router. But that's okay, because it's a really good router. It comes stuffed with all sorts of great software. You name the protocol, it probably supports it. It probably even supports Apple Talk, if you ever remember. Okay? What we're going to do with this fantastic, wonderful product from Cisco is we're going to take the brain in it and rip it out. All those fancy protocols, all that clever intelligence, all that sensing of its environment, we're going to pull it out. And we're going to create a product that we like to call the Pika 8. It's a 3922 box. We're going to sell it for about $11,000. Okay? Less than half the price of the Cisco box. The Pika box doesn't do much. Now it routes packets really fast. So a packet comes in, it looks at where it's supposed to go, and it throws it out the back end very fast. But it doesn't know any routing protocol. It doesn't have fancy management capability. It's got very little in terms of software on it. Okay? But that box is cheap. And guess what? Once I stick it in my network, there's no smarts in it. I'm not going to have to upgrade it because it doesn't do anything. Now this is what a traditional network looks like. We talked about this, right? We've got our 6 routers all interconnected. That's a network to us today. In the world of SDN, what we've done is we've ripped the brain out. We've placed it into a centralized server, and we've connected that server to every single dumb router in that network. And that giant central brain is doing all of the thinking for us and telling those routers what to do. In a nutshell, that is SDN. Okay, a very interesting point about today's modern routers. They all have CPUs in them. But what's interesting about those CPUs is they're about 2 generations behind. They're slow. And oh, by the way, those CPUs, They're doing a lot of stuff. They're doing management tasks. They're doing housekeeping tasks. They're not completely focused on routing packets. Okay? If you take everything and put it on a Dell Infinity server with a zillion gigs of RAM, it's sitting in the center of your network. Guess what? That Dell Infinity server is like 8 times faster than any CPU to have actually any of the routers. It's going to be able to do everything that you want it to do faster, quicker, and better. Next slide. Let's talk about how networking is done today. This is effectively a router broken up into individual parts. So vendors provide routers. Vendors work very hard to provide a very good router. Okay? The functionality starts at the lowest level. This is the specialized packet forwarding hardware that every router has. Sole purpose of this hardware, have a packet come in, do a quick lookup to figure out where it's supposed to go, and shove it out the back door. And do that as fast as you possibly can. Okay? There's not a lot of distinction in that. Everybody sort of has the same chip to do that. Where things start to get interesting is when you move up to the operating system. Every router, every vendor has an operating system. This is ultimately the crown jewel of the vendor. Okay? Cisco has iOS, Juniper has Junos, everybody else has flavor of it. On top of the operating system are the individual applications. These are the applications that are doing things like routing and management and failure detection. All those sort of fancy higher level things are running out here on the top of the third level. By the way, yes, it is. Next slide. All right, so let's dive into routers just a little bit more deeper. This is going to be the hardware that you're going to find in a router, okay? Once again, at the lower level, we've seen this before, we call this the data plane. The data plane exclusively is dealing with real bits, packets, Ethernet headers, things like that. It has the task of processing packets that are received. When a packet comes in, the data plane grabs it, uses its information about the local forwarding state, where should I send you, okay, and then it throws it out the back door, okay? If you're going to decide to forward a packet, you better know where it's going to go, and you better know which one of the computers that you're connected to is actually going to get it. In order to make sure that they're coming quickly, the data plane has to operate at top speed. Okay, sitting on top of the data plane is what we call the management plane, which is effectively the CPU on the router. The management plane is responsible for coordinating the action between the data plane and the control plane. So the control plane, once again, that's where all of our fancy logic is going on. This is where we're going to compute the forwarding states. Where should I send it? Has it changed? Has somebody failed? Has somebody moved on? Have we replaced a particular device, etc., etc. Now we are at the top of the hour. I can sort of wrap it up now. If you want to move it forward. You're here, I'm here. You gotta leave it already. Alright, go to the next one. This is just abstraction. It's basically saying that today's networks are built on top of an unreliable infrastructure. We all know about that. We'll go to the next one. So what's the right way to construct a router? If you were going to build a router today, what's the right way to do it? This is effectively it. Take all of the stuff that goes into a router today, consider that just simply to be the data plane. Only have a router worry about grabbing packets, figuring out where they need to go, and shoving them out the back door. That's it. Take all the higher level fancy stuff and push it off onto a separate server, okay? A high-end box that's optimized to do one thing, to calculate what's going on in the network. Okay, we're going to do this one more time. So this is our little network diagram. We've got a group of switches. All the switches are interconnected. Next slide. We're going to work in a little bit of the control functionality at this one time. We're going to have what we have in a network is a distributed algorithm. So each one of these servers are working with the other servers to figure out what a complete end-to-end path of the network looks like. Next slide. That's a lousy way of doing it. We found out why, because there's challenges and difficulties. A much better way to do it is to introduce what we're going to call a network OS, operating system, a network operating system. It's going to sit on top of all of our servers, okay? What it's going to do is it's going to have a discussion with each server in that network, and it's going to be able to build a complete picture of what that network looks like. Next slide. What this means is that your network operating system is going to have a global view of the network. Remember, that's something that none of these routers down here have. Okay? then once you have your global view of the network, you can have a control program sitting on top of that that manipulates that global view, makes changes to the global view, which then gets rippled down into the network. If anybody in here is into software, you should be getting very excited right about now, okay? Because all of a sudden, you've got a model of the network. And it means that you can do programming things with that model. When you change the model, you will change the network. Get it? All of a sudden, we're talking about network programming. Next slide. Okay, here's a little quick show. So in this particular one, I've got user A here, and I've got user B in the lower right-hand corner. Here's the rule. A cannot talk to B. A is a boys' boarding school. B is a girls' boarding school. They should not be permitted to talk to each other. Configure the network to do that. What are you going to have to do here? You're going to have to configure each one of the, 8 switches in this network, right? Do not allow A to talk to B. Hey, you're really going to have to visit each one of those switches and tell it A cannot talk to B. Next slide. Hey, look, it's the world is seen by the Sdn programming layer. Remember, that's the layer sitting on top of the network model. It says, hey, I've got this network thing, and here's a whole bunch of people who are plugged into it. A's plugged into it, and B's plugged into it. So what's the program going to say? Hey, A can't talk to B. Poof! End of story. And then all the lower layers will worry about what that actually means. All the lower layers will worry about configuring the actual network. But you don't have to go to each router and say, A can't talk to B, because the network will take care of it. Oh, so the layers of the network. So really, this comes down to the software thing, right? So you make your changes in the control program. Okay, there's this virtualization layer that has the job of taking the changes you make in the control layer, mapping them into the network view, the current state of how the network is. When you make a change to the current state of the network, then all of a sudden you have to communicate out to the individual routers what that changes. You have to reconfigure them. But remember, you're operating all the way here at the top level. You're dealing with a model of the network. You don't care about the individual boxes because you're seeing the network as a whole. You're seeing the network as a fabric. Next slide. This is how a telephone company sees its network. It's a little complicated. I apologize for that. So this is the cost of switching to Sdn. Because remember, if you switch to Sdn, you have to replace all your routers. So there is a cost associated with that. This is the cost of today's networking equipment. What's important on that is notice it's going up. And our network's getting smaller or bigger. It's getting bigger, right? Okay. So if the cost of the equipment that you're putting into the network is getting bigger and your network's getting bigger, are you spending more money or less money? Not only are you spending more money, you're spending a lot more money. I think AT&T spends about $9 billion a year on network equipment. That's a lot of money. Okay? This is service provider revenue. Most important thing on that, it's a straight line. So yeah, they're making more revenue, but they're not making a lot more revenue as their networks get bigger and bigger. They're dying. Because as their network costs go up, all of a sudden the amount of money they're making is going down. The beauty of Sdn is if you go ahead and implement it, your opportunity to make money goes sky high. Just think of all those out-of-work Russian missile scientists out there. If they could program the network, what would they come up with? What fantastic things could you do if you could come up with a programming language that allowed you to dynamically reconfigure a network based on what was going on? We don't know the answer to that question, but I'll tell you what, it's going to be pretty amazing when somebody starts to figure it out. Next. Hey, Google! Who's ever used a Google product? Any hands not going up? Oh, you've never used a Google product. Okay, yeah. Okay, yeah. Just a little slow on the hand, but that's better. All right, so here's the scoop. Google has done some pretty incredible things. 2012, their vice president of engineering showed up at a conference and said, oh yeah, so we're into this Sdn thing. Oh, by the way, we've done it. We converted one of our networks, one of our 2 backbone networks, one of the 2 networks that runs our company to Sdn. Quiet in the room. I'm going, what? Sdn, we're just talking about it. It's like an idea. We're just like kicking around the idea of Sdn. He said, yeah, no, we're done with it. We got it. It's in. It's running right now. Okay. Now, what's even more amazing about this is there were no Sdn vendors. It's not like Google went out to the Sdn shop and said, I'll take one of those, one of those. They had to design everything. They had to design the hardware. They had to buy the hardware. They had to design the software. They had to go out and buy the software. So what they do is absolutely amazing, but it speaks to the power of Sdn. Google's willing to pull the trigger and say, listen, what's going on here is so valuable to us, we need to move on it before the market gets there. Next. A bunch of stuff. This just shows the costs that go into running a network. It's really freaking expensive. Next. Now, we talked about this one when you have a failure. Google was pissed off about network failures. Google had 2 problems every time a network failed. Okay? Number 1 is that it took time. It takes time to repair a failure. And oh, by the way, if everybody tries to use the same link and then you have to go back and you have to do it again, it takes more time to repair a failure. And that, the longer you're down, the more upset your users can go. The second problem that Google had is when you have a failure, you're going to rebuild your connection. Great, that's wonderful. What's your network going to look like after the failure's been fixed? The interesting question is, you can't tell me the answer to that question, because potentially it's going to look different every single time. It's non-deterministic. Maybe one goes to E and then it takes the 40 link, or maybe one goes to E and it takes one of the other 40 links. Okay? You can't tell me which path a given application is going to use, because it's going to be a little bit different each time, and maybe it's dependent on timing, who got there first. Google hated that. What they wanted is deterministic solution. Every single time there's a failure, I want to rebuild the network, and I want it to look exactly the same, assuming the same set of inputs. Next slide. This is the solution that Google came up with. Take all the smarts out of the routers, stick it in a centralized traffic engineering application running on a separate server. Have that server talk to each one of those routers and tell them what they should be doing. This is what Google's backbone network looks like. Google actually has 2 separate backbone networks. One is their iBone network, which I think is their internet one. That's what we get Gmail and YouTube and all that sort of stuff off of. Standard network built with standard Cisco, Juniper gear. They have another one they call the Gbone network, which is their Google back one. They use it to communicate between their data centers. That is the network. They went in and they replaced the standard switches with SDN switches, Openflow switches. Next. This is what the data center looks like. They've got a data center network. It's tied into a couple of Openflow switches, a couple of SDN switches. Those switches are then tied into the long haul paths. But that's okay. We're going on this slide. Okay. This shows what their data center network looks like. This is the network. They've got some cluster border routers, basically routers on the edge of the data center network. Those cluster border routers then talk to a bunch of switches that communicate with the other data centers. Next slide. What Google did was they went in, they dropped in a server, and that server is running a bunch of different applications. This is where my vocabulary already starts to fail me. On that particular server, we had Quagga, which is a suite of routing protocols, because you need to have your routing protocols. Nice little suite got dropped in there. There's OFC, which is the Openflow controller. This is the program that's controlling all of your SDN routers. It's programming and updating them with the routing information that they need. There's another application called Glue that allows OFC to talk to Quagga. And then there's another one called Paxos. Paxos is used to basically resolve who's in charge. Because this is so critical, they had multiple parts to the system. They had multiple components to it, and so they needed to have this component to be able to figure out which one of these multiple systems is actually running the show. Who's failed, who hasn't failed, who's in charge. Okay? Over here, you see actually the switches that they were using. Because they're blue, that means that these are all standard switches. What Google did, and this is a classic problem, you already have a network. You love SDN. You want to convert to SDN. How do you do that? How do you get from here to there? What Google did is they replaced half of their switches with SDN switches. Okay? So they were still using blue switches. They're still standard switches. They operate just like they always have, probably from Cisco or something like that. The yellow switches are actually their Openflow switches or their Sdn switches. They started to use the separate router, separate server in all the individual programs to do the programming for the switches. That's fine. Eventually, they went ahead and replaced all of the switches in their particular data center with replacement stuff. Now, the awkward part about this is after having done all this work and having done it very, very carefully so they didn't break anything, Google was left with the situation where now everything in their data center worked exactly like it always had. There was no improvement because all they'd done was replace without breaking. Next slide. This is when things start to change. They added a traffic engineering module. So this was the module that started to be able to set up connections that were optimal across their network. This was one that was able to respond when there was an outage and build quickly, one time, the correct reroutes around the breakage without having to figure out or to attempt to rebuild types of connections. The addition of this suddenly made the whole SDN effort well worth it. And that's just one application. There's a lot more you can add on top of that. Next. This shows basically in any given data center, you're going to have application 1 through 10, application 1 through 10. They're all going to want to talk to each other, right? They're all going to have differing types of bandwidth requirements and stuff like that. So you're going to have to balance it. Next slide. This is a quick snapshot of what Google's data center network looks like today. You've got a whole bunch of traffic sources, which is basically applications. They would all like to use bandwidth on the network. They all have to report into this traffic engineering and bandwidth allocation server. There's a bandwidth request collection and enforcement agent, sort of like a traffic cop. He collects everything. What do you want? Who do you want to talk to? How much bandwidth do you need? Tell me, okay? He then passes it on to a bandwidth broker. The bandwidth broker is in charge of implementing Google's corporate guidelines. The guideline could be like, we don't do backups until it's the middle of the night. So we don't even try asking someone during the day. Or if we're doing a backup and all of a sudden a high priority request comes along, scale down the backup and scale up the high priority request. Once they get that all worked out, it goes to the traffic engineering server, which communicates with the gateway to the actual SDN site, and everything gets updated. Next slide. All of this is possible because of something called the Openflow Protocol. The Openflow Protocol is how the control server talks to the actual SDN router. There's nothing special about Openflow. It is one way to do this type of communication. There's a lot of vendors out there that have said, screw Openflow. And they've come up with their own proprietary implementation. Is Openflow going to be around forever and ever? Don't know. It's too early. If people are excited about it, what it basically means is you have your controller up here, it talks to the actual switch down here. There's a bunch of flow tables. Flow tables are simply lookup tables. Have you seen this type of packet before? Do you know what to do with this type of packet? If you do, great, go ahead and do it. If you see a packet that you don't recognize, reach out to your controller and say, man, where did this come from and where is it supposed to go? Remember, the controller has a view of the complete network, right? If you're getting packets and they're supposed to go someplace, that controller knows where they're supposed to go. It will tell you what the next hop of that packet is. You can update your flow table, and next time you see a packet from that source, you'll know exactly where it's supposed to go. Next. This is just more detail on Openflow. We can go on from this. There's some more detail there. This talks about what happens when you receive a packet. Packet comes in. Do I have a match? Have I seen this type of packet before? Nope. All right. There's something called a table missed. If I have never seen that packet whatsoever, what should I do? You can program it so you can take some action based on that. There's three things that happen when you actually receive a packet. The first thing is that you update your action set. Next is that you update your packet match set field. And then you update your metadata. Basically, you keep counters. How many packets of that type have I seen? What it means is every switch has a limited number of forwarding entries it can have. It doesn't have an infinite amount of memory to store this stuff. So if you have a bunch of packets that you haven't seen in a long time, you can strip them out of the table and replace it or something. Right next. Controllers. So the controller is such an incredibly important function in an SDN network. You're probably going to want to have more than one. Okay? When you have more than one, you start to get into complex situations. There's three types of controllers: equal, slave, and master. There's three types. This is an equal controller connected to a switch. Equal controllers have read-write access to the switch. They can do anything they darn well please. You can have more than one equal controller connected to the same switch. You can have a slave controller thrown into the mix. A slave controller has the ability to read what the current status of the switch is, but it cannot write to the switch. And finally, there's a master controller. The master controller is always right. What it wants to do is what happens, it beats out any controller every time. Okay? The amount of communication that goes on between the controller and the switch can at times become huge, right? Depending on how many packets that switch is operating. Remember, the switch has hardware that's optimized to receive and process packets. So they may be coming in there very fast, and if it's just starting up or if it hasn't seen a lot of the packet, it's going to be sending a zillion messages to the controller. What it means is that the pathway between the controller and the switch, you can set up multiple pathways. You have to start with the main pathway, then you can build out more auxiliary pathways, which just basically means you have more bandwidth. Okay? If anything happens to that main pathway, then you have to tear down all of your auxiliary pathways. Make sense? Next. The future. So this is the cool thing about SDN. If we were here talking about Ethernet, you'd be snoozing, right? Ethernet's been around for 30 years. You really have to work hard to come up with something new to talk about when it comes to Ethernet. SDN's been around for maybe like a year or 2 years, not very long at all. Right? Means we really don't have the answer. So the future is wide open for everybody next. One of the big questions when it comes to SDN is, look, I've got a network and it works. Yeah, this SDN stuff is probably quicker, better, faster, and I would love to work it into my network, but how do I take my existing network and work SDN into it? We don't really have a fixed answer for that. This shows that there's sort of 3 different approaches. One is the dual stack approach, and arguably that's what Google did, right? You run SDN and you run your standard one side by side with each other. Another approach is to work SDN in around the edges and treat the core of your network as being legacy. It's sort of a lump, if you want to think about it that way. And you put all the fancy new functionality around the edges of it. Another approach is called Panacopia, and this is a little complex, but basically you integrate your legacy and your SDN portions together. What the guys who are doing this research have discovered is if one part of a connection is SDN, you get the benefits of SDN. So you don't need SDN on both ends, you just need one end to be SDN to get the benefits of what SDN can give you. Next. So, a lot of companies have data centers. In fact, a lot of companies have multiple data centers. To interconnect the data centers, they've created WANs, or wide area networks. Well, there's a problem with those WANs. The links between data centers are really expensive. Okay? But the problem is the utilization of those links is generally speaking at about somewhere between 40 and 60%. They're wasting a lot of really expensive bandwidth. What happens is they ask for, let's say, 100 meg, and they end up using between 40 and 60 of that 100 meg. There's 40 meg that nobody's touching, right? And why is that? Well, it's because the applications they have say, well, I might need this much bandwidth, so I'm going to reserve it, right? Because someday I might need that. Do they always use it? No, they're generally using a smaller portion of it. If you implement SDN in that particular environment, you have an opportunity to do much better bandwidth utilization. You get bigger bang for your buck. The bandwidth that you have, you'll be able to control and you'll be able to use it at a much finer grade. Next. Reactive and proactive flows. Basically, either you've seen a packet before, you don't have to worry about it, or if a new packet comes in, you have to talk to the controller. Next. How do you handle all faults? Basically, you ask the controller, say, hey, I've had a fault, and the controller says, that's not so good. And it sends new routing information out to every router in the network. Next. So here's a huge issue with SDN networks, a fantastic area for research. So, if the network's just sort of humming along, it's not that heavily loaded, I can get away with maybe, one server running my controller, and then all of a sudden everybody wants to watch the Super Bowl using streaming video over my network. Oh my God, really? Okay? So now all of a sudden my network usage goes right through the roof. I need more than one controller. I better be firing up a bunch more controllers, right? And as I fire those controllers up, I better be taking the servers or the routers that were controlled by that one and handing them off to these brand new controllers that I just fired up, so I can distribute the load of managing this network across all of these servers. Oh, thank God. Oh, look at that. The Super Bowl ended. Everybody turned off their streaming video. Okay, now all of a sudden I don't have much of a load. So now I'm going to have to shrink. I'm going to have to shut off those extra controllers that are no need, and I'm going to have to take all those routers that were distributed over those other controllers and bring them back under the control of one or just a couple of routers, right? So the scalability issue is huge, and we don't have a good answer for it, right? But it's so critical because that controller runs the whole network. All right, this is it. This is my last slide. This is all I have for you. So when you're thinking about SDN, you have to understand we do not have the answers yet. We're starting to get a better grasp of what the questions are. Questions right now fall down into three basic areas. The first one is interoperability. Okay? Networks are not new. We have a lot of networks sitting around, right? Now you're coming along with your shiny new SDN technology. That's fantastic. But I already have a network. So you're going to have to tell me, how do I take your shiny new SDN technology and work it into the network that I have without breaking the network that I have? And how is it going to make my network better? Right? Good question. We don't have an answer to that. Scalability. Oh my God. Okay? So you can see in an SDN network, things like the controller are critically important. It's the central brain, right? Well, I better have enough processing power in that central brain to handle my network as it is today and my network as it grows. So do I just build it on a faster platform? Do I use multiple copies of the controller? Oh my God, if I'm using multiple copies of the controller, do I have to have them intercommunicate somehow? How do I scale an SDN network? And finally, reliability. You know, I don't want my controller to fail, or if it does, what should I do, right? Maybe the controller doesn't even fail. Maybe I just can't talk to the controller, which is sort of the same thing as failing, right? How do I handle that situation, right? Maybe a particular switch or router becomes isolated, okay? It's not down, it just can't talk to anybody. How do we handle that situation? Good question. We don't have answers to those questions yet. It will get answered. In fact, probably get answered 4 different ways, right? But we're going to have to see what ultimately the answer is that people want to run with. Because these are all very, very wide open. If you're interested in SDN, this is the time for you. Okay? People are just starting to dive into SDN. You'll see that there's a bunch of little companies out in California getting snapped up for millions of dollars, because that's where they're out in California, right? But we're on the edge of trying to figure out what it is. Cisco doesn't know what to do. Juniper doesn't know what to do. AT&T doesn't know what to do. Verizon doesn't know what to do. But they all know they have to do something. Because, as we said at the beginning, SDN changes everything. Thank you very much for your time. Deb, you did a fantastic.
You might be asking yourself, where do I go from here? The ability to effectively manage an IT department and to do it well is a skill that your company needs you to have. It sure makes sense to invest the time and energy that it takes to become a great CIO. A simple way to start doing this is to sign up for the free The Accidental Successful CIO newsletter. This monthly publication is sent to your inbox and is overflowing with tips and techniques on how you can spend your time making the right IT decisions and really leading your department's IT professionals. We'll cover how to evaluate new technologies, how to foster relationships with other parts of the business, how to hire the right staff, how to work with the CEO so he understands just how critical IT is to his and the company's success, and we might even cover a few CIO career tips or two. Hey, the newsletter is free, so you can't go wrong there. In the description of this video, you'll find a link that you can click on. Go ahead and click on it, and you'll be taken to a web page that will let you sign up for the newsletter. There's even a free gift in it for you when you do. Thanks for watching this video, sign up for the newsletter, and congratulations on starting your journey to accidentally becoming a successful CIO.